Okay, hi everyone. Today we talk about causality in the Sheaf-Theoretic approach. Okay, this is what the talk. The talk depends on the this article about the Sheaf-Theoretic structure of definite causality by Gugeso and Binzani. Okay. Okay, so let me remind you first of all the Sheaf-Theoretic approach to contextuality and non-locality. Okay, what we did before 2 weeks ago. Okay, but I have to remind you. So what we have actually this phenomena that we have some context. Okay, I have some measurement. Okay, so okay, we have this context. Sorry. Like some measurement, but they have some intersection between them. Okay, some measurements that they have intersection between them, and we do this measurement as we can do. Okay, so sorry, not this point. I want sorry for this. I already described this, but I want to describe this in another way. So just a minute. Yeah. So okay, let's start from this point that we have a section like for every we have some set. Okay, X is a set. Is a set. So let's say what we say that we have just one set of outcomes. This is a set of outcome. Is a set of outcome. Okay. This set of course it can be like we can call 0, 1, 2, something like this. Okay, until n. Okay, sub-zero of outcome. And what we described last time, we described this pre-sheaf of section. Okay, let's call this section. I will call this section. What is this? This is going actually for every subset of this. This is all the subset of X. Give me some set. Okay, how it's work? It's like subset of this going to all the maps from this subset to O. Okay, this is actually all the maps. Sometimes I know it's okay. No, it's okay. Sometimes we will use this, like I will use this home from U to O. Okay, all the maps from. We describe this all the section. Okay, and we say that this is a pre-sheaf. In I will describe like it's to be understood for you also what we're doing. This is a pre-sheaf in this sense. Like if I have now, okay, I have this U. Okay, so I have some map from this U to O, some outcome. Okay, for every element of O, I have some, like let's say that O is 0, 1, 2. Okay, this is O, the set O, and I have another map from here to O, from some V to E to O, and they have some intersection. Okay, they are the same intersection. Maybe I have here A, B, C, and I have here A, B, C, A, B, A, D, E. So the intersection in A, B, they are have the same. Like in the intersection, this is map, one map. let's call this map phi and this map psi. And this map phi and psi are the same. If I take the intersection between u and v, they are the same. Okay, let's say that this. So we can say that this is actually a map, one map from the, like this coming from one map. Let's call this map maybe some map psi tilde. This coming from one map from the union to O, right? Actually, because okay, if they are the same in the intersection, like okay, A going to A going to 0 here, B going to 1, D going to 2, E going to 0, and the other map here, this is psi, and the other map phi, A and B going to the same places, okay, and maybe C going to 0. So we can describe this information by one map here that send A to 0, send B to 1, send C to 0, send E to 2, or D to 2, send D to 0, right? For one map. But actually, it's not happen when I apply here the distribution. Like, okay, I compose this section with the distribution. So what is the distribution factor? This is a functor. Okay, maybe if someone don't know what I mean by functor, don't care about it. Maybe you don't know what is functor, right? Okay, don't care about it. What is this? Like this send every set here, every element here. What is element here? Subset of x. Okay, this is all the subset of x. This notation you know maybe, right? This is all the subset of x, like every u inside x. Here, element here. So this send to set, but also if we have some v inside u, this also send me map from, but now inverse map. This is called contravariant functor. Okay, this send me map from here to here. Like for every what its element here, it's a map from u to O. What its element here? It's a map from v to O. What is the map from? Is a restriction, as I did here. We need this to describe this phenomenon. Okay, to describe this phenomenon. So actually, inside of this, what is this? Like we can think about this. Inside of this, there is like a map from here to here. What is map? That's just inclusion. But every map going to map, but in the inverse way, like a map from UO to VO, okay, which is just like phi going to the restriction of this, okay. But also we have also the inside this we can do intersection, we can do union inside this, okay, and this is important to describe this phenomenon, that if I have two section, we call like two things here, like one from OU and the other from V. Okay, V not included in U in this case. That it's have the same, are the same in the intersection. They can come from something from the union. Okay, this we have. But if we apply now the distribution, the distribution functor, what is this distribution factor? I described the last time that it's give me from every set, for every set, like for example set A, dA, it's all the distribution on A. Okay, from finite set, let's say. Okay, but it can be from any sets, but let's say from finite set. Okay, when I say set, I mean all the finite set. We're just talking about finite set in this talk. Okay? So the what is this? All the distribution maps on A. What is distribution on A? Just like this is A1, A2, A3, like this. It's just I give some distribution on this A. This quarter, this half, this 0. The sum is 1. Okay, so this is distribution like a map from here to 0, 1. such that the sum of them over all A is 1. Okay, this is distribution. Also, this actually not just apply on sets. It's also applied on function. Like if I have now function from A to B, some function from A to B, one can describe the function from df from dA. Now it's not in reverse. Okay, now it's direct, like what's called covariant functor. So okay, if I have a map from here to here, it's give me a map from dA to dB. Here, no, it's inverse, right? If I have a map like this, I can think about this as a map from V to U, the inclusion map. It's give me a map from applying the section of, okay, let's call it the sections, from the sections of U, like all the outcomes on U to the section of V. Okay. Here, what is this map? How we can describe this map? It's easy to describe. Like, okay, I described last time, but let's do again. It's again like if I have some distribution here on A, like some distribution, it's going to distribution in B, but it depends what is the map. Like, let's say that the map from A to B, like this is B, and the map F send both of this to B and send this to B1 and send this to B. Then if I have some distribution here, distribution in this, like something like A1, it's again quarter, something like this is a quarter, this is half, something like this. What I did before, the sum wasn't 1, right? Maybe I was wrong. Yeah, right? Yeah, no. Okay, so here I have a distribution. This gives me a distribution. What is that? Just come from this. So this will be the sum of this, because this to the preimage of this, so this will be half, and this will be half, right? It's coming like the distribution here. Actually, I have P distribution here. The distribution here, df of P, it's given to some B. It's depend who is. I will give P of all the preimage of this. So I going all the P of A, where A it's a preimage of this P, like f of A is equal to this specific P. That's what we did here. Okay, like this half, it's from quarter plus quarter coming from. Okay, but here actually we don't have this phenomena we showed the last time, that if we now compose these two functors, like I have the section functor from here to set, and then I compose with like this section going to set section, sorry, functor, and I compose with D with the distribution, then I going to set, because this like this give me for every subset of X some sets, and then I apply the distribution. So actually this like some subset here going to all the distribution on the outcome. Okay, all the distribution, like all the or in other all the distribution on maps from U to O. Okay, and this we need, because we describe some phenomena, like we have some. What is this describe from physics? Let me remind you. Like I have some events here. Event O, we can say that here is people, Alice, Bob, and Charlie. Okay, this have some measurement to use. Measurement A, measurement A prime, measurement A prime, and this have some measurement to use. B prime, this also have some measurement to use. And every time we take some, this choose some measurement like this. Okay, this choose this measurement A, this choose this measurement B, this choose this measurement. Okay, and this will be a context. We get all the outcome. We interested in all the outcomes they can get, like home from A, B, C. to suppose that all of them get the same outcome, like oh, all of them we can get the same outcome, or it's just 0 1, for example, like electron plus or minus, okay, something like this. This is the measurement, and we interesting on all the outcomes they can get. This is exactly the section of, this is exactly what we call the section of ABC. Okay, all the outcome of this, like map from this to 0 1. Okay, and if we sometimes, okay, we don't have, like every time we do this experiments, we have another outcome, we have another result, but we can do it many times. It's what we described last time. We can do it many times and get a table of probability. This exactly be something here, like some distribution. If we do it many times, like every time, okay, I get some result. If I take this measurement with this measurement with this measurement, and I get some result, A going to 0, how many result I can come? This is just finite result. B going to 1, C going to 0, for example. This is the result that I get. How, okay, if I did this million times, how much time I get this, I ask. And then I have a probability table, like I have a distribution. Actually, I have P distribution on this. Okay. I have a distribution on this. And what happened here, actually, we ask, okay, we have this, like, there is no connection between what they're doing. So we expect that if I doing now something here and this distribution, I restrict. We can restrict here, like I restrict on just A, B. So I get some result. Okay, I get the result, but it's the same if if I did this for, if I take the context to be A, B, C, and I restrict this to, like, okay, let's call the distribution Q that I call, and I restrict this to A, B again. So I have to get the same result, okay? Because, okay, this is like A, to do A, B, it's not depend whom I do with, okay, with this measurement, because these people don't know which one I do with. Actually, so this describe maybe more general, what we did here describe more general things, but actually the experience coming from something like this, the physics experience coming from something like this, like we can think like here we have some events, okay, and we all the time take one from every one, like this is a subset of measurements. So our x will be the union of all of this, like all the measurement we have here. This is our x, okay, our x. But every time we take u, not all the u we're not interested to do. Our u will be like take one from here, one from here, one from here, okay, and we do together. But we expect this, what we called the last time, the non-signaling, because there is no signaling. Like, okay, C, we don't know what happened in C, like B and A. So if we do this, like maybe it's the right way to write it, not P and Q, like P, it's when we did A, B, C together, and here when we did like the measurement with this. But when we restrict it to AB, like what I mean to restrict it by AB, what I describe here. So if I want, for example, to compute here, what is the probability to get this 0, 1, 1, for example, 0, 1, sorry, because I restrict it to AB. So I can do this, like ABC 0, 1, 0, like all the plus, all the things that I got with C 0, 1, 1. Okay, like I take all the things that I have probability here 0, 1. Okay, but I can do this not with C. I can do this with C prime. Okay, I can do this with C prime, or with C I will get the same result in probability. Why? Because A and B, like if I choose here A and B, they don't know who you choose here, so they have one result. Okay, this is the idea. So actually the Sheaf-Theoretic, I try to back to this a little bit in some way, but it's depend on what we describe. It's in other talk. It's in the YouTube if you want to see this. Okay, it's in YouTube, you can see. But I hope, yeah, I can able to describe it in a good way. But actually, what not they not include here in the Sheaf-Theoretic approach, that if what can happen if we have signaling, like what can happen if this like have signals this like this, like say this Charlie told Bob that I already use this, or I use this, then it should change. I can't say that this will be the same. If I used like C or C prime, it will be the same. Then we don't have this non-signaling. We have signaling. Okay, like if we have. So this is the idea of this article of this paper, to to describe this phenomena, like with this phenomena when we have signaling, when we have arrows, some arrows. Okay, like I have this also, like this signal, this something like this. When we have this, how to describe this, but also in this way, in Sheaf-Theoretic way. Like what is Sheaf-Theoretic way? As described, that we have in the section, this is really sheaf. We can, like, if we have some information that are compatible in the intersection, maybe we have more, like, okay, we can have, I just described for 2, but maybe we have more like that is compatible in the instruction. It's coming from 1, but after applying the distribution functor, it's not like this. Okay, and we already show some example last time. It's not like this. So we want to describe this phenomena with when we have such a signaling, to describe it like this causal. They called it causal because this causes, like the outcome here caused by what happened here. Okay, if we have such things. So we want to describe this in this paper. They describe this in the same language of sheaf and pre-sheaf. Like we have something sheaf, but when we apply the distribution, it's become not sheaf. Okay, so we have the phenomena of conceptuality. Okay, what is the idea? Okay, what is the idea behind this? Actually, I didn't say this, but let's say that if we have this, if we have this, like AB, okay, let's maybe just take 2 of them because it will be easier for me to write it. Now, if we have this, how we can describe the compatibility and this scenario, what we have? What is the scenario? Like I have Alice, Bob, and Charlie. And every time I can Alice use some of his measurement of his input, like he use this or this. Okay, he use this or this one, he use this or this one also, he use this or this. So actually we have how many contexts we have here, like 2, this 2, 2, 2, like 8, right? A, B, C, or A prime, B, C prime, something like this. We have 8. Okay, we have 8, but we can actually write this 8 in this way. All the contexts that we have in this way, like I can write A, B, Okay, let me write it, and then I can describe what that means. Here I have a triangle, here I have a triangle, here I have. Okay, here I don't have, it's not fields, but C prime, right? So here also we have triangle. Like here, there is 8 triangle. You see, there is 8 triangle. And this, like this triangle, what I mean by this triangle, I mean the context that I choose A prime, B prime, C. Okay. And here, this, what is this? This mean like these two triangles, this triangle and this triangle have this common in them because we already used this here, these two measurements, the same measurement for Alice and Bob here and here, right? So we can describe the scenario like this, right? Right, like everyone measurement. But actually, if we have a measurement, if we have something like this, okay, maybe let's, okay, this for this. But what if we have this, for example? What if we have this? This I described last time. This is just this, right? A, B, A prime, B prime, A, right? Just this. Okay. But actually now, because if we have, sorry, if we have some signaling here, for example, so I can't say that I have a B, B to A the same as this, because actually this one will affect him what A choose, because he know there is signaling. Okay, this Alice, right? He إشارة كونداردي like this. Okay, so Alice can tell what's happened. So I don't. So I have to write like this. This A. Okay, I have this context, but this context is not A. It's AB. Why AB? It's B. Actually, we mean by this B, this measurement. But why AB? Because I want to remember that here Bob knows that he used this, but he know that Alice used this, and this can affect his outcome. Okay, and the same now for this, like, okay, when we go like this, here will be A prime B, right? Because this is B actually, with this represent B, but this is not the same. This actually coming to represent B, and this coming to represent that Bob uses this input, this measurement B, but not the same, because here Bob knows that Alice used A, here Bob knows that this use that Alice use A prime, and the same here. Okay, the same here. If I want with P prime, the same. I have to, okay, do P prime with here P prime with A prime. Okay, the same. So this is not the same. Okay, not like this. This it's happened when we glue this together, right? Because we think this as the same measurement, but now we have to think about this as different measurement. Okay, and here why we didn't do this, because there is no signaling, like okay, A is the same A, it will be the same A, because he don't know what Bob you used, right? So this will be the same. This is the whole idea of the paper, by the way. This is, but we can like we can describe this
here. You're assuming that Alice is somehow earlier than Bob, right?
Yeah, exactly. They said it can happen from time, like maybe something else also, because they have also, like, after that they talking about this, like they have signaling and they have signaling, so it can be in the same time, but they are both in the same area of each other. It depends. Maybe one can think that it's coming from things like time, like this happened before this, and we know, and maybe because one in the area of the other. I don't know in physics they do this. Yeah, you maybe. Yeah. Yeah. So this is the idea actually behind this, and we will see also this what happen if we have signal. We will see some example later, but let's now show how they do it in the Sheaf-Theoretic approach, not just like this. Okay, let's grab. Actually, here it scans the section. Maybe in the first paper they do it's like common outcome for all of them. But sometimes it can be like here in some experiments that it's not like Alice have his outcomes, set of outcomes, like 0, 1. This have another set of outcomes, like plus, minus, something, 0. This have yeah, okay, so it can be like this. So the section have to change, and this actually just for the Sheaf-Theoretic approach. They do this, they change the section that they said, okay, the section it's like this, that you going to, because every x can have his outcome, every x in x, every measurement have his outcome. Here actually we are interested in the case that every event has its outcome, okay, every event. But sometimes even every measurement has, like this, have another outcome than this. It can be like this. So what they do, like this will be not like one set, this will be a bunch of sets. Like for every x there is an outcome for x. So actually we send this to this u and u. Like for every, what is this? This is a problem. Like something here. It's what is this? It's like some outcome here in O x. It depends. Like okay, if u is x1, x2, x3. So what is this? This is O x1, O x2, O x3. Okay. So what everything's here? What is this? This is exactly like some outcome from here, outcome from here, outcome from here. Okay, it's exactly that, because sometimes it's not uniform outcome. Like if it's even uniform outcome before what I did, if it's uniform outcome, or what I did this, home from U to O, but actually I can write it like this. This is exactly this, like O U times, right? For every U, this is exactly this. But actually here, maybe it's not the outcome. So we can write it in this language. If it's not the outcome, we can write it in this language, okay? Okay, so we need this. Sometimes, so the section, even in the old pre-shift, it can be like this. It's okay, no problem. So the first things we want is the local. What is the local? Like before we have this x, before actually we have this x is the local of all the measurement. Okay, like I have this scenario. Okay, we can describe now scenario by this, right? CD. It's not all scenario not have to come from such in the Sheaf-Theoretic in such experience. It's not coming from such experience. Like we have some event, but this is a scenario that we do this together, context, and this together, and the x is all the measurement, right? CD, right? This is the local, like all the measurement, and here is the scenario. So what we take, like our local, like to take all the context that include all the context is all the, sorry, I wrote this because I don't want to confuse with the probability. This, all the subset of x. This includes all the context. Like this context, what we do the measurement together, this context, this context, this context. Includes all the context. But now we have different, actually we interested in such a thing. We interested in when we have like events, and for every event, we have some event like this. Some event, and for every event there is some set of measurement here, or of output, like let's call it IA, and there is outcome, some set of outcome here. There is some set of outcome, some set of input out, output. I see B here, B, sorry. I see here it's coming ID O, OD. Okay, and we have here some signaling, right? like we have this maybe signal, maybe this send signal to this signal to this. Okay, so we need okay. Can see this. Yeah. Thank you. Okay, we have some signaling. Okay, so actually let's define it. What is our scenario now, or what it's called? It's causal definite scenario. It's called. Yeah, this is called, yeah, definite causal scenario. Sorry. Definition. A definite causal scenario is the following. Sigma is I, O when is a poset. A poset, what we mean, it's a partial order set. Like this is exactly like in this case, in the example, this example. This is A, B, D, C. This is the tau. Okay, like partial order set. We need it's the event. Where is the event, and what is the where we have signaling, where we don't have. Like here we have signal from here to here. From here to here we don't have. Okay, so this have to be partial order. Like you know what it's partial. Like it can be like we have also maybe I didn't draw, but we have signaling from A to B to D. Okay, it's because it's partial order. So we need this. We need I to be what it's I it's all the outcome for everyone here. Like I is I omega for every omega here. Okay, like what we see here for everyone, we have IA here. All the input here or the measurement. Yeah, right. And we have also set of input. Like it's a vector, I call it a vector because it's like this. In the paper, they use vector like this, like in this side. I don't know. I like to do this. To do this, okay, for every omega. So we need this, okay, and then our local, like where we choose the context, or maybe it's something that include more the context, because actually let's look, because we want what we want to imitate what happened here. This is not all the context, right? But why we need this to why we need this as a source of the section? Why we don't just put just the context? Like I have this, for example, yeah, in this example, okay, why I do this? I can just say that I have just A, B, C, A, C, all the context, A, C, I don't know, yeah, or C, D, A, C, something like this. Why I need all the subset? I need because we want to describe this pre-sheaf phenomena that we want to the language of union and instruction. We want all the instruction, all the union to be with us. Okay, we want to be free to do this. So that's why this actually from here to here it's functor. Okay, from here, like we want this to be our source because we also do union here and intersection. Okay, so now what will replace this one? This is the things. What will replace this one? Let me describe in example, and then I can like what replace this one. It's just chosen. Okay, let's say this is the IA here. This is the IA. let's say that this is A prime, A2 prime, here B prime, here C, D prime, something like this. So it's all the subsets that I can choose, but from here, like from what is all X, it will be this, all of them. But not every subset, it's okay for me to choose, not every subset, because I don't want to, if I choose this, I want also to choose something from here because it's affect this. There is a signaling. So actually, the subsets, like all the things that I want to be here, it's something like this. Like this is okay to choose subset of this. It's okay, subset of this, subset of this, but it's not a subset of this. This is okay, for example. This is, or all of them, like it can be the subset, all of them. This is okay, but it's not allowed to choose, for example, this and this. This I don't want to be. Like I can think about the union of them as is our subset, but it's okay to say as a vector because we want to know that this is coming from A, this is from B, this is from C. And this is not allowed. Why? Because here I take in B, but I didn't take in something that affects this. Okay, what affects this? We will see this. We will see this later when we talk about the compatibility. We need these things. So actually, our local for this, the local will be the following set. Okay, I will describe what it's mean exactly, but let I omega, but without the empty set. Here omega, it's in this delta. So what is this? What I mean by this? Let me explain these things. Actually, this is actually all the order, all the suborder, like subsets of this poset, but that include everything lowest. Like in this, okay, in this example, for example, I can choose this to be A, B. It's okay with me. A by itself, it's okay. A, D, B, it's okay. But this, for example, C by itself, it's not okay. Why? Because I want everything before. Okay? So, okay with this? What is this? I can give you the, but I talk, it's not to give the correct definition, but you can understand, for example, what we mean by this. Or they call it the lowest set. They include the lowest sets. Every subposet, but includes the lowest sets. This is not include here. Okay. For example, the BD also not include because it have to include also this. So we take from the union of this. Okay, we take some order, like how it's look like object here, like U here. Actually, the vector U is an object here. It's a vector because at the end of the day we take something from here, from the product. Yeah. So I can look at this as a vector. But what is this vector? Like we have to choose some lambda delta. This is called lambda. Lambda. We have to choose lambda U, lambda for this U. Okay. If we choose, then we choose some subset from every omega in this lambda U. Okay. Subset, but this subset have to be not the empty set. Okay, because not the empty set. Okay, like for every this lambda, what is this lambda? This is lambda for this U, specific for this U. Like for example, what I choose here, like this. This is some element in this one, in the local. This way, it's okay with this to choose this. Okay. The local actually include what is the local, the idea of our local. We want it to choose all the context, and this is choose all the context. What is our context? Our context is just to choose one for everyone, right? We describe this. Our conscious choose. This is okay to choose one of every one because that the whole poset is include because it's a poset is include. It can be the rule of delta, right? Like I can choose this A, B prime, C, D prime. This available, right? This available. No problem with this. This is available, and this is our context that we're interested in later. Okay, to do the experiment in these things. So this include our concepts. Also, this include intersection and union. So let me convince you that this intersection and union. And of course, is the important things also. This is also by itself is a poset, like by itself have inclusion. Like if I have one, so the included in this also is there. Okay, so this will be also good to have. So not yeah. So it's for example the inclusion. It's okay, right? The inclusion, like this is a poset. Like we have inclusion here. Like what kind of inclusion? Like it's okay. Maybe we call it as a vector. Let's describe using the example. It's a bit things like this. For example, B. This is inside A prime, B prime, C. This is inside this. What it's have? So the partial order that corresponding, let's call it U, and let's call it V. So the lambda U actually it's inside lambda V, because here lambda U what is just A B, and here I took from A and B and C, right? And also the subset like this inside this subset. Okay, all of them. This included in this is included in this. Okay, so there is like there is order here, the inclusion. This is what we have here. We have the inclusion. We have intersection. Of course, we have intersection. What is the intersection of this both? This, okay, because this is yeah, like intersection. What it can be the intersection?
Can I ask a question?
Yeah.
I'm a little bit confused. So I thought when I was looking at the context, like if A comes before B, then I can't just have B be a context because I always have A coming before it, right?
Yeah.
But here you're writing just B on its own.
Yeah, we will describe this with the outcome. Yeah. I will describe. Now it's so far okay. I described before what is the hidden idea before this and how we can describe it as they didn't do this actually. They did it formally like this, and then at the end you can understand why they do this. So far it's not obvious, but yeah, I will explain this why we get to this idea. So far I just explained this. What replaced this? But then I also have to describe what is the functor. The section factor will be different, and then it's and then I will explain this what happened. Okay, so what we have here. As the intersection, it's easy. It's to see that if I have, for example, A, don't know, B prime, B prime, C, for example, intersection with these things. Just a minute, like with what happened? Yeah, I can. Here is the thing that I can here choose something like if I choose here A prime, for example, B. Okay, D. I can do this. I can do right. D prime. What is the intersection between these two? Like here, we don't have something in D here, right? We don't have something in B. We have, so it's just A, B, and it's available to B, right? Yeah. We can think about this the whole union of it, but we need to be careful why we don't think about this as a subset of the union of all of them, because we need to be careful with the order. We can't choose like BD. It's not good because it's have to include someone from here. Yeah. So this is, and the union, one can imagine what is the union, like what is the union of this again. Okay, the union of this, one can do as exercise. It will be also available, like it will be in the sets, because there is some assumption on something to be here in this, right? Okay, so we have the union we have, so we can talk about the like what is in the other like, limit and co-limit we have. This is the things like we have. This is what we want. But here is the union and the intersection. What I want now to describe this. Okay, describe what is this one from here to here. Okay, to describe this one, let me define before causal. What is causal map? Okay, because actually we need these maps to be causal now. Okay, so if we have given a poset, this a poset, just a poset, like just A, B, C, D, C, like this, just without the sets. And if we have some sets like this, like the outcome and the outcome, like if we have some sets, other sets here, and we have a map like this. This is the sets you can imagine. This is the inputs for every. This is the output for everyone, and a map from the product of this to the product of this called causal if it's preserved, like what happened here, like what is this, if the outcome, like what with this map, let's describe this map from product of this to product. So it's give me from everything here, like let's say that we have three here, just like I have, this is my this is my omega, like it's omega 1, omega 2, like ABC I described before, omega 3, this is the one. So I have just this 3 here. If I have just this 3, it's going to some 3 here, right? Like this is f of A1, A2, A3. But what is f of A? It will be something B1, B2, B3, right? So actually this will be causal map if this one, for example, B2, is depend just if of everything, of every outcome here input before that coming before the 2. Where is the 2? This, like what's coming before or in, like everything from here and before, like it just depends. This will be just depend on this 2. It's not depends on this. Okay, this is the definition because of the order like this. If I don't have a order, for example, if I don't like this also poset, it's a discrete poset, it's called, like we don't have any signaling, any order. So what it will be, this will be actually depend on everything here and behind it. But what it's behind this? Nothing. So it's just depend on this. So this will be depends on just this. Like for example, f of something x, y, z, in this case will be the same of if x some. Sorry again. Yeah. If I have f of x, y, z, it will be the same as this. This will be equal because we have the same, even if this is different and this is different, this is the same. If we don't have any signal. If we have such a signaling, like this, then I know that this will be the same like this. If I have the same xy here, so the output will be the same. Sorry, in the second place. Sorry, in the second place. I mean, in the first place also it will be the same. Yeah, in the first place it will be same. Let's take it formally, and then I can describe some examples. This is like this is so important and so important definition. Like once understand this definition, then can understand this paper. So it's called this map. It's called causal. If how I can write it carefully. If okay for every omega, like if I take some omega in this, then if of a1 okay, it's called it some I here. If of I omega in what I mean omega, like I mean in the place omega, f of I in the place omega, because f of I will be here. There is a many of omega. This is specific omega. Maybe let's call it like this. Okay, some specific omega. So then if I choose, then this is depends only on I when I restrict I, like I, when I restrict I to every omega behind this one. Okay, yeah, like what I explain here, like it's depend on this, not on the, yeah, or in other words, okay, maybe let's say is in other word, if I have other word in other word, if I have two vector, okay, I and G, and these two vector are the same in every for every omega. If I like if I take that this one is the same for every less than this one, then the outcome of them will be the same for in omega. Okay, of this or of this will be the same in if I put this or this omega tilde we use in this place. Okay, you want to ask something?
Yeah. So in the example you had before, A1, A1, A2, A3, f of A vector equals B1, B2, B3. B1 can only depend on A1. B2 can only depend on
No,
A1,
in yeah, right,
okay,
right,
and
right, right,
and
right.
then
Yeah,
and then B3
B1.
can depend on all three.
Yeah.
Okay.
Depend what is yeah. Let's give some example and see what happened actually here. Let's describe this example that we have. Okay, this is ABC. This is, we could describe this is ABC. So this is tau we have. Okay, this one, and let like a omega a. Sorry, I called it A again. Sorry, it's maybe not good to call it A. Okay, omega 1, omega 2, omega 3. Yeah, and I have a omega 1, omega a map from here to omega 3. Let's say, okay, let's say this map to be omega, okay, to 0, 1, 0, 1. This is the one for omega 1, this is the one for omega 2, this is the one for omega 3. Maybe this is easier to understand this way when I give some specific. So, okay, let's say, okay, also this one, like this is A prime, this is B prime, this is C prime. Okay, so what we have actually, it's always like it's one of the, this is a property of the limit. Like map from here to here, actually the three maps, like it's a map from, every map from here to here, it's actually three maps. Like this map for the first thing, and this map and this map. You know, you already took calculus. Yeah? No? Yeah, you do. Sorry. So you like one give you this map from R3 to R2, and they say this map is sinus x, y, z, e, x plus y, something like this, right? So they give you two maps, actually. They give you two maps from R3 to R. Yeah? This is exactly, actually. This is what is the map? One map from, it's not, this is important, that here R2 is, so one map to product of things. It's the same as map from sorry, two maps, one from this, one from R, one from R. This is two maps from R3 to R, right? So this is what I use here. Like, okay, this one map here is actually three maps. Okay, let's call it F omega 1, F omega 2, because it's the what it's get in the first one. It's the second one, F omega 3. But actually, what we say that these maps it just depend on what this omega 1, right? So I can think about this map as the map from, like, this map is exactly a map from a omega 1 to 0 1 omega 1, right? Because I can collapse all of them. Like, okay, I have here maybe F A B C prime, but this is the same as this gets 0, for example. But then I know that all of this gets 0, like this gets 0, this also 0, and all. Oh, if I change here, it's the same. So I can collapse. I can think as this map just from A omega to this, right? And this one, I can think about this as a map from A, because of the order. Again, if the order is not this, it will be different, right? This map, it's a map from, sorry, A omega, and I have everything before, okay? So actually, every map like this is three maps. This one, it's depend, the value here, the third value, is depend on everything before. Maybe I answer your question before. You will say that we need to, yeah. So this exactly because we need the outcome in this. It's not depend on the input here. It depends on the two inputs, and this depends on the, yeah. So how is this generalized actually? How is this generalized the idea here? Okay. How is this generalized? What happened here? What happened here actually? What we have if we don't have signaling, like if the order is discrete, what will be? It will be like this. That this is depend everything less than W. This is just W, so it will be the same. And this, like the value here, it will be depend just on this, because nothing before this. There is nothing giving signaling to this, so it will be like this. And this one will be like this. And this is exactly actually what I describe here. Like for every one, like, okay, for every one, we will take, like, for, okay, we have now our set, it's A omega 2 with A omega 3, okay? And we will get for this, like a map for this, but the outcome will be from where? From this one, like this. So this is the map, like to the outcome, just one maps. But the difference here, that what I describe here, is that everyone, we have different values of outcome. So it can be, because it's the same 0 1, it can be just a map to 0 1, okay, from this to 0 1. That is, okay. So actually this generalize this one if we don't have in the discrete case. Okay, yes, your question. Yeah, omega 2. I have omega 2, of course. I erase omega, and here omega 3. Yeah, I erase the wrong things. Right. Yeah. So omega 2, omega 3. Right. Okay. So this actually generalizes this section, but we are different here. Like when we don't have like anything here. Yeah. Even for subset, even this one, like if we don't have, if you can think about this, if I take all the omega 1 with this, and take this definition, is the same as all the subsets because we don't have order, we don't have any assumption. Okay. But if we have order, what I described before, so let me continue. Okay. Okay, so what we define now, we define this section to be, okay, I didn't define this yet, right? But you can understand what is the section now will be. Like for, again, I have some definite causal scenario, this definite causal scenario I have, and then we define this functor from here, this, you remember what is this? This is a take, but with the order. I have this, like here I have IW manises, I have input, okay? And I describe this to set, okay? Describe this to set. How I describe this? Like everything's here, U, what is U? This is a vector. Like I take some collection of U from some for some omega, but omega to some like good order, like sub order, but it's good, like have all the lowest ones. We send this. Now we send this to the section of U. What is the section of U? It's all the maps from the product of U omega to the product of the outcome. But of course, we ask the F to be causal. Yeah, what I describe here. Yeah, what I describe here. And now, what is empirical model? Like, what is the empirical model we know before? It's some distribution for every context that's compatible, right? So it will be the same. It will be the same. After define the section, that is how we define now the empirical model. Okay, definition. Empirical model, maybe we did it before, but I mean by empirical model, like when we did the experiment like million times and we get then probability tables for everything, for every context, probability tables that compatible with each other. This is called empirical model, like every probability table like this. So empirical model actually in this is empirical model E is an element in this one. But now I take not any U here in section, I take U to be vector, like one measurement from every event. Okay, I have this event, I take measurement from here. This is the I that I going through. Okay, so I going through all, just a minute. Yeah, where it's I coming from, this is I omega 1, I omega 2. So it's something in the product of this. So it's in the product of I omega, which for all, I going for all. This is like element here. Like what it's element here? is some distribution on the section of this I, like, okay, let me maybe like this. So some element here, like for every vector, like this vector a, B, C, it's a section there. Actually, section just choose outcome for everyone. Just choose outcome for everyone section. We don't have here the assumption. The assumption doesn't work here because we have just one vector here. Yeah, this that causal. Okay, it's not appear here, but it's appear in other place. I will describe. Okay, so section of this, like all the outcome on this, but distribution on all the outcome. Distribution on all the outcome. Like I have how many outcome for this we have? If it's just 0, 1, 0, 1, 0, 1, I have 8 outcome. So distribution in this 8 outcome, which I can get from some experiment, right? I do it every time I get something, I did it a million times, then I have this table. So this, but okay, for every outcome, like if I change, I have another, like with that with the product. Okay, I have another one. If I change, like it's A, B prime, C, something like this. Okay, it's another one. But it's compatible, yeah, such that it's compatible as we describe in the same sense that we described before. Okay, such that it is okay. It's look like that what we did here actually, the where appears this causality, like here it's not appears the causality again, section, all the section of I, but it's just it's the map. Yeah, okay, it's the map from these things, like what it will appear here if I choose I, just one things will appear here. So just choose a number here, just choose outcomes. So the causality, it's nothing to do. Okay, just causality if I have more than things. If I have two more than one thing in the source, then it can be something, say something, but it's not say anything. But what say things? It's a compatibility. The compatibility here, it's not the compatibility that we have before, because actually we don't have all the compatibility in here. We can choose where we are here in this, like then I apply this D. Okay, so we are here, but here I don't have everything like I have before because it depends on the order. Yeah, so let me in example I can show what happened here. So maybe let's start with let's start with this example. This because actually we work on this. If we don't have signaling, this give me the CHSH scenario. Okay, we have 0, 1 here, the output here also, the output is 0, 1. When we don't have is discrete is exactly the CHSH. But what happen if we have this one? What will happen here? Actually, what is the section that we have? Let's say what is the section that we have. So section here, or global section, like let's say what is the global section? We have the global one. What is the global, like the biggest one in here? Before, when we have peaks, the biggest one in this order, it's X. But now when we have this, the biggest one is the product of all of them, right? So actually the section, it can be from I A, let's call it A, I B, which is like section of this A B prime. What is this? We ask a map from, it's just a map from here to here. But when we ask about right? A map from here to here when we ask this map to be causal, right? So actually, when we ask it to be causal, we already saw this, that this is exactly like a map from to this one, that this point A is just depend on this. Like it's a map from here to here, to 0, 1. And it's a map from here to here to 0, 1, right? So from this to this and this. And this here appear what the idea, what we said before and what we wrote before. We wrote it's like this, right? This A prime, this have P and P prime, this have another P and P prime. Actually, what we called it, we called it A P prime. We called it A A prime P prime. This, yeah. So this B. Okay, this exactly appear here. Like okay, outcome is exactly what we know as from this scenario. Outcome from this scenario, global outcome from this scenario, just to choose outcome for everyone. This is exactly what we're doing. Like outcome for A here, outcome for A prime, and also outcome for every two of this. This is the 4 that appear here. So this is like actually they show that this the simplicial, okay, the sheaf-theoretic approach not includes this, or maybe let's call this simplicial complex, but actually everything you can do like this. I will show another examples. But here, what happened, this is the important thing. What is empirical model? Like here, I can have this to be empirical model. I can show you. Yeah. 6, 1, 2, 2, yeah. 2 and 6, right? How many? 2, no. 6, 2 and 6, because this in our way, how many contexts you have here? Like for everyone, how many section you have here? Sorry, for everyone you choose 0 or 1, 0, like this. Yeah. Actually, this can included in the even in the simplicial approach. This can included like this is the scenario you have. Yes, that is. Like this is our scenario. This and delta Z2. This is our scenario. Okay, now okay. So this is empirical model. I want to show you that the number, by the way, the number of contexts doesn't change. You see, the number of contexts, it doesn't change if I have this signaling, because how many contexts we have? It's just choosing vector, like A, B, A prime, B, A, B prime. The number of contexts doesn't change. What it changes is the compatibility. Like we don't have here compatibility because we have to think about this as different and here as different. That is, so that's what makes the section more section. Yeah. So, and here actually, like maybe I wrote example, so it's better than try some. Yeah, I wrote some example like this one: quarter, half, quarter, 0, half, 0. This is empirical model here. Why this is empirical model? So here it's coming the definition. Okay, it looks the same. Okay, you just took distribution, for distribution in this case. Here distribution, here distribution, here distribution, here distribution. Like I mean here the 0, 0. What is the probability to get 0, 0? We had this language before that. What I did. Yeah. Okay. Sorry. Here 0, 1. Here 0. Like this. All the distribution here distribution. But the compatibility, we see that we don't have here compatibility on B because we don't have to have, because here we can restrict this one, we have to restrict here, but in this one we don't have B by itself. Like we don't have this is not here. B, it's not here. Why it's not here? Because we say what is this, this have to be something with all the allowed set, right, in the order. So B can't be. When I give you some example, maybe the example it's the example is there here, yeah, right? I say that C can't be, right? It's not the order, so I can choose here. Okay, I erase this example, but I think it's coming from something like this, A, B, C, D. And I say that in this one, I can choose just C by itself or B, C. Because I, first of all, I have to choose this delta, and this delta have to be something that have all the lowest things. So this is the idea that you have to impact. So in the definition of the empirical model, it looks like, okay, it's the same, but here is the thing, the compatibility, it's not the same. We have compatibility on A, but we don't have on B, because you don't have this B here, or B prime. You don't have this here. It wasn't allowed, and one can see this in the picture, in this picture. Like this, in this empirical model, because we know that we have just this and this. We can just this separate it, right? So here in this case, we don't have anything contextual. We know this in this case. Okay, let's give another example. Like this example, A, B, C. Okay, we see actually we can do the same. Okay, let's say what is this, what is compatible, what it's not. But actually we can, to describe this scenario, we can just describe the simplicial complex that tell me the context. So what we have this here, for example, before, like I have this before, right? We have A, B, C without the discrete one, and this was this one, right? Right? This one, like triangle, 80 triangle. Here we still have 80 triangle. We still have 80 triangle, but what we don't have actually, what we have here actually 80 triangle, but more, we have more measurement, like, because I have to differ between measurement, like, okay, again, okay, I didn't say what it's this, but I all the time take just 2 from everyone to be easy for us to describe this example. So actually what we have here, we have C prime, we have this, sorry, AC prime, for example, and we have, this is different. This is the thing. This, both of them C, but are different, okay, because of this. And what we can do actually, the easier things to describe this, let's describe this both, first of all. So both of this will be like this, C, B, C prime, B prime. This we know. All the option we take to take 2 of them. And then, but the A, it's different. Like I have here, sorry, maybe, no, just a minute. Yeah, I wrote it or not, this one. This is this, right? Yeah. So I have, now I see. Yeah. This A, I going to this, but this is not going to this. So this is C A, right? Because it's coming from A and there is signaling from this. So I have to defer this one and this and this, all of them coming from A. So I have this for context, but in the other side, I have this for context, all of them to A prime, right? Right, so this will be, for example, A prime B, not B. This will be different than this. This again, like this one becomes this one. You see what is the difference? Yeah, like some compatibility we ignore. This is what happens, that it's compatible, but it's the compatibility, it's not the same compatibility because we have signaling. Okay.
So we know that this scenario is non-contextual because of Borobaya, but it's just too
Yeah.
cyclic.
Yeah. What about this? This is contextual, by the way.
Yeah.
Because it includes some, yeah, something this. Yeah, it's include. Right. Okay, the other example we can do is this example when we have the same. I again take A prime, B prime. Okay, A, B, and C going to C. Both of them going to C. It's again remind as this, like this, but we have less compatibility. So what we have here, actually, again, I prefer to start with this because this we know. This is this A, B, A prime, B prime. But now for C, there is like, okay, AB, for example, I going to, because this depends, the C, actually this C will depend in both here, depend in B and in A. So we have C, some C here, okay? And we have, of course, C prime that depend on A and B. This is a triangle. This is a triangle, okay? We have another one, like here, we have C and C prime again, but it's not the same, even if it's the same B here, but it depends, this C depends on A because both of them, send off signaling. So this one, even if it have the same B, C, but because not the same A, so this will be another triangle. You will see what happened here. It's nice, like a nice picture. It's A prime, B, C prime. And we have another two triangle. Like this, we also, again, did compatibility. So how we did this, I can see, I don't know. Now, by this, right? By ignore this. Yeah, off of them here. Like C is the thing of C. Like here, the C, it's become something different, and C prime. So here we did the belief because the C got signaling. And here we did it for B and C. In the things that describe B and C together, we separate this because both of them have signaling. Yeah. So actually, what I think it's, again, it's one can describe this just by, instead of this, one can describe this just by including this in some in simplicial complex, like, okay, described by simplicial complex by this idea just to use, and then the same outcome. You can see the outcome is the same, the empirical model is the same, because this tell me everything. This tell me the compatibility is different. But now you can't say that this here compatible in BC. No, we can't. Sorry, which one? This and this. Like this context and this context, we can see that this have to be the same age because this actually C and this is C. But no, this is not the same age. It's not compatible here. Yeah. So we have here more less compatibility, less, but we have more section in this when we have signaling. Okay, I have maybe 2 minutes just to say that in some proposition later, what they doing actually, they describe how we can describe empirical model directly, not as like here what we did. The empirical model is the same definition, but we can use causality to describe empirical. This is the thing that we told me about. So empirical model can describe like this. Some empirical model is a map from here I omega to D of the outcome, okay, such that this map causal, okay, this empirical model such that P causal. So what it's mean causal in this, because it's not the same as we described before, but in the same things, like before what we described, we say that this, for example, from A, B, C to something OA, OB, OC, when we have this like A, B, C, this, we say that this causal if what? If the F in A, B, C, for example, if I take this one and I do to A, B, something here, is the same as F, A, B, C prime when I restrict to A, B, again, this is to A, B, right? But this restriction we have here also, we can restrict some distribution. What is the restrict sum distribution? Is to take the sum, as I described before, take the sum of everything. So here we can say the same definition, like what is the causal if I have P from here to the distribution of this, what is to be causal? Like to be like this, if I take P of A, which is give me distribution here, and I restrict it to AB, just take what is this outcome give me, and take the sum of everything here freely, is the same as this. So, and one can check that the causality is the same as the compatibility. One can check, in this case, the causality is the same as the compatibility. Like it's a good exercise to do this, like when we have discrete. Then what is the causality? We have everything. Then for the causality, we can do everything. This is exactly the non-signaling, because we can restrict to everything. But here, causal is depend again on the order that we choose, the signaling. And the signaling cannot give me that I can restrict to everything. Like here, I can restrict to BC, right? The same as the compatibility. Okay, that is, thank you.